So we've talked a little bit about igneous rock identification. We've talked about how you can generate magmas. We've talked about the two different settings in which you can have igneous rocks form, and that is either they can be intrusive or they can be extrusive. So now we're going to focus in a little bit on the intrusive rocks, and we're going to talk about the sort of features that they form. They're called Plutons, and so Plutons is our next step along the way here. So, and again, you can see a photograph here of Mount Rushmore and the Black Hills of South Dakota in the southwestern corner of the state. And that's the Harney Peak granite right there. And so granite is, again, it's a phaneritic rock. It's one of these that cools deep inside of the earth, okay? So it gives it time for it to crystallize into slightly larger crystals. And with that granite, of course, you're going to get some feldspars. And you're also going to get some quartz. And so quartz and feldspar are the two major constituents of a granite. And you'll be able to see the crystals. And so that's what that rock at Mount Rushmore, that's how it crystallized and came to be. When we talk about those intrusive rocks, everything that we know about them is either from indirect evidence or we have to get it from the ancient record. In other words, we can't go down to a modern magma chamber and understand it, okay? So sometimes we can image that with remote sensing and things like that. Things like seismic, it gives us a clue as to what's going on in a magma chamber. But in fact, when we try to understand what they look like, we have to go back to the ancient rocks. And so we're going to talk about the different types of Plutons. And these have been described at various places. So I'm going to show you some examples, and I want to explain a few terms. Of course, in geology, really what we're talking about is learning a new language. It's a language by which we can communicate what we understand about the processes that operate on the Earth and the sort of products that we get. So a couple of terms I have to talk about first. One of them is called discordant. Discordant means that it's something that cuts a bed. And so if it cuts a bed, it is going to be considered to be discordant. And so discordant means you can cut a bed. So in fact, if you have sedimentary rocks, which are commonly bedded or whatever, the igneous rocks very commonly will eat into those rocks and cut those strata. And so that's a discordant sort of feature. So most igneous rocks, in fact, are discordant. We'll talk about a couple that may be considered to be concordant, actually 3 of them that are considered to be concordant. Concordant means, that, of course, it doesn't cut the beds. And so those beds are there, and the magma will just kind of push in between beds, and that's pretty much what it does. It pushes in between the beds and doesn't cut them, in other words. So the Plutons are the bodies of igneous rock that intrude into these rocks. And so Plutons are those sort of features. And they can either be mafic, or they can be felsic, or they can even be ultramafic if you're in the right sort of setting. But mostly when we talk about these things, we're usually talking about something that's either mafic or felsic or maybe intermediate. And so those are the sort of features we're going to look at. So here's a list of them here. A batholith. A batholith is a discordant feature. A batholith is something that intrudes into rock, and it has to be larger than 100 kilometers. And we're talking about like looking down on it in map view. So 100 square kilometers in length, it's like that's going to be 10 kilometers by 10 kilometers, but usually they're even larger than that. And so these are things that are sort of like across a state or something like that. So for instance, in California, we're going to talk a little bit about the Sierra Nevada batholith, but there are other batholiths as well. There's one in Baja, California. There's one in the coastal areas of maritime Canada, and so in Western Canada. And there's one in Idaho, the Idaho batholith. And so those batholiths exist in various places across North America and across the world for that matter. But a batholith has to be discordant. It will be discordant, let me put it that way. And it's also larger than 100 square kilometers. So 100 square kilometers, kind of the break-off. Because anything smaller than that, we're going to call it a stock. And so a stock is a much smaller igneous body, very localized compared to a batholith. And so batholiths may constitute entire mountain ranges. A stock, on the other hand, is going to be a very small sort of feature by comparison. So it's less than 100 kilometers in size. A sill is the next on the list, and a sill is one of these concordant features that pushes out and pushes into and in between strata. And so a sill is kind of table-shaped or flat, in other words. and it will actually raise the beds up or push the beds down below, and it intrudes laterally into rocks. And so that's what a sill is. And so I'll show you some examples of that. So a sill, it's like a windowsill. Windowsills are flat and relatively horizontal. Well, most other sills, they don't have to be horizontal, but they can be horizontal, and they always push into other beds laterally, sort of. So that's what a sill is. A laccolith and a lopolith, I'm going to lump these two together. They're kind of a special situation. Normally, I don't even think the book even mentions these two, but these two are concordant also. But if you can imagine something like a mushroom where it kind of pooches it up, okay? So that's what, like a sill, except it's got a little thicker middle part in it. And that's what a laccolith is. A lopolith is just the opposite of that, where it's relatively flat on the top. It forms like a bowl shape down below it. And so that's a lopolith. Lopoliths and laccoliths, they occur in nature in a few places, especially in the West. And they're not real common, I guess I would say. So they're in Western North America. For the best example I have of this, and there's actually 3 or 4 of them out there in Utah. And it's the Henry Mountains in Utah, or the LaSalle Mountains in Utah, and then also Navajo Mountain in Utah. Those are all examples of a laccolith, and so kind of mushroom shape. So it kind of intrudes into the igneous rock around it and kind of forms like a mushroom sort of shape, sort of kind of domed shape underneath of strata, but it has strata down below and strata above, and that's a laccolith. Lopolith, again, bowl-shaped. Now, the next on the list here, they're real common, and those are called dikes. And dikes are discordant features. Dikes will actually cut right across the beds. And so very commonly with laccoliths and lopoliths, you have to have some sort of feeder dike that goes into it. You have to be able to get the magma from some lower depth and allow it to get into the rocks to intrude them. And so very commonly a dike will allow that to happen. So those are called feeder dikes, where you can feed the magma into either a lopolith or a laccolith, or into a sill for that matter. Typically, stocks and batholiths can also have dikes, but very commonly it's where the dikes will actually cut all the way across, the sill or some other sort of feature here. So either the stocks or the batholiths as well. So dikes are discordant and kind of tabular in shape, kind of planar and tabular in shape. And then lastly, we've kind of talked about this just in passing a little bit. There are volcanic necks as well. And so volcanic necks are discordant as well, as you well know, because the volcano would have been around them at one point, but then the volcano eroded away and it left the remains of what was feeding up into that volcano. So our example for that, in fact, is Devil's Tower in Wyoming. So in Devil's Tower, you get the volcanic neck, and technically there's a stock down below that. And so that stock is where the intrusive comes up, fed into that volcano, but right at the surface, right near the base of that volcano, that's where you get that columnar joining, and that columnar joining indicates that it was cooling pretty much inside the volcano itself. And so there's a stock down below and the volcanic neck above. So that's the list right there, and it kind of gives you the definition. So that's pretty much it. And so for the rest of this talk, I'm going to show you how common these things are. I'm going to show you what they kind of look like in cross-section according to an artist's rendition of this. And then also we're going to look at some examples then. So we're going to look at examples of all these sorts of features. So in the next slide, you can actually see what, and they're actually numbered on here so you can identify. There's a laccolith at the very top up here. And you can see that there's a feeder dike down below it, right? So that's that wide feeder dike that fed into that laccolith there. But it pooched those beds up. It didn't cut the beds, however. Now, the dike did cut the beds down below that, but the laccolith itself does not cut those beds. You see a sill in number 5, and number 4 is the feeder dike that goes into that sill. So number 4, you can see where it cuts the beds down below number 5. But number 5 itself doesn't really cut the beds. It just kind of pushes the beds out of the way and intrudes laterally into that bedding plane, essentially here. Number 3 is at the very base, and it's everything that's down there. And so that is a batholith. So they're going to be pretty large. So in other words, the one feature that they don't show you in this diagram, and they could have probably done that, they could have shown you what a stalk looks like. And so, but they didn't want you to get confused between what a batholith and what a stalk looks like. So you can see a volcanic neck at number 6 there. That's at the base of that volcano there. You can see a lapolith, which is kind of bowl-shaped again, as number 7 there, with the feeder dike down below it as well. And there's a couple of other small dikes that are shown on here as well. Number 2 is one, and there's one that's not numbered just below the number 5 there, if you look to the right, and then just above the batholith there, you can see that. So you also see that there are intrusives on here. That's everything that is numbered. And then there's the extrusive, which is the volcano above. And so after we finish talking about Plutons, we're going to go on to volcanoes. Volcanoes are a little bit more exciting because there's a little risk involved with volcanoes. So we're gonna look at that a little bit more closely in the future here. So that's going to be next on the list, in fact, after the Plutons. So if we looked at the intrusive igneous rocks across North America, they're shown in purple on this diagram, and of course they're showing you the topography as well. But you can see in the west coast, there are mountains that stretch all the way from Alaska all the way into Central America. And so that's called the Cordillera, in fact. And so the Cordillera is a whole series of mountain ranges that are kind of bundled together on the western part of North America. And then also you can see on here an area in northern Canada that's loaded with these things as well. Well, that's the ancient continent of North America right there. And those things date back billions of years, okay? So most of those are at least 2.5. Some of them are a little bit younger than that, so maybe 1.8 or something like that, billion years. But they can go back all the way to like 4 billion years, some of those, close to 4 billion years anyway. So that's the area in Canada around Hudson Bay. Now, this is interesting. I'm going to give you a little heads up on why that is. That area was glaciated during the last ice age. And what that glacier did, it scraped off most of the sedimentary rock that's up there, left a little bit behind, but not much. And so it got all the way down to the core of the continent. And so that area we call the Canadian Shield. So the Canadian Shield, we're going to talk about that a little bit more in detail when we talk about the structure of the continent. But that is the Canadian Shield in the Canadian North up there. But if you look in the west, that's the Cordillera. And so the Cordillera are these strands of mountains that go, well, like in Colorado there, right? So those are about 1.4. If you went to California, those are only about 200 million years old. I say only, but, that's nothing to a geologist, okay? So 200 million years roughly for the ones that are in California. They go back maybe to Jurassic, some of those. Jurassic and Cretaceous, some of them. And you can see the purple rocks that stretch out along the western part of Canada as well here. And so those are all batholiths for the most part here. You can see the ones in Idaho as well, above the Yellowstone hotspot track there. So it's hard to see that, but it's a little groove that's cut across the Cordillera there. So that little groove or flat space that's in southern Idaho there, just above that is the Idaho batholith. So next on the list here, we're going to show you what that looks like up close. Here's some other, you can see the Coast Range batholith up there in California. You can see the Idaho batholith down below that, or excuse me, I said California, I meant British Columbia there. So that's the Coast Range batholith, but below that you can see, and to the right, you can see the Idaho batholith, and then where the white arrow is pointing here, that is towards the Sierra Nevada batholith. And so the Sierra Nevada batholith is really the roots of the Sierra Nevada mountains. And so the Sierra Nevadas are in the eastern part of California, right on the border between Nevada and California. And here you can see some of the, looking from an airplane here, you can see looking out towards, you remember Mono Lake, right? We talked about Mono Lake when we talked about magmas and we talked about Mammoth Mountain in that ski area, right? Well, Mammoth, that's a little bit north of there. So that's Mono Lake up there on the upper right, on the middle photograph here. And you can see that these things have a sort of pinkish cast when you're flying over. Snow-covered, of course, that's Sierra Nevada. Snowy mountains, essentially, is what that means in Spanish. You can see North America's highest, the United States' highest mountain in the continental United States, and that's Mount Whitney here. So that's Mount Whitney on the right, upper right here. And so that is made out of granite. That's the number one thing that makes up the Sierra Nevada batholith. Granite. And so here's a cross section. Now this is a little confusing because you have to kind of look south here is what you're doing really. And it's showing you east on the left-hand side and west on the right-hand side, but this is something that is on Wikipedia. So I don't have to worry about stealing somebody else's artwork on Wikipedia. Here it is. And what it's really showing you is the Sierra Nevada batholith here. And it's related to subduction on the west coast. Well, that subduction isn't happening anymore in California where the Sierra Nevada mountains are, but it is happening where the Cascade Mountains are, up farther to the north in Oregon, Washington, and the southern part of British Columbia, and actually northern part of California too, but not here in the Sierra Nevadas. So where the Sierra Nevada batholith is, you have to imagine there were once volcanoes over those magma chambers, but the volcanism stopped. It stopped essentially when the subduction stopped off the west coast. So in fact, in the past, California was riding over the Pacific plate. It no longer does that. That stopped about 17 million years ago. And the next thing you know is like those mountains were uplifted and it eroded away much of those volcanics. And so what it left behind, in fact, were the granites that had intruded down below. And so here you can see kind of a cross-section of what it would have looked like in the Sierra Nevadas several million years ago, but that's what it is. If we look at it today, when we see the mountains in the Sierra Nevadas, they're absolutely stunningly beautiful. This is one of our national parks. It was one of the earliest ones. It's not the earliest one. That happened to be Yellowstone, but this is one right here called Yosemite. And regardless of it's Yosemite, Yosemite, Yosemite National Park. And they're made out of granite. And this is like a climber's mecca right here. So what you see over here is, I think that's Bridal Veil Falls right here in the foreground on the right-hand side. And there's a place called Glacier Point not far from that. On the left-hand side, you can see the highest cliff in North America. And it's a little over 2,000 some odd feet, and that's called El Capitan. And so El Capitan is in Yosemite National Park, and in the far distance back there with the head of it just tucked below that cloud there. That's called Half Dome. And so Half Dome has been eroded partially by glacier that once went through this valley and gouged out the entire valley, and it left half of that rock there. And the other half of it had spalled off, and there was a rock fall at one time and was moved out by the glacier, but that's called Half Dome in the far distance in the back right there. That sheer face that kind of overhangs. So let me try to show it to you this way. It's that sheer face that kind of overhangs like this in this image. And so that is Yosemite Valley. There's another valley just to the north of this that's just as spectacular as this, except they dammed it up, and they use it for a water resource now for the city of San Francisco, and that's called Hetch Hetchy. So Hetch Hetchy Valley was a lot like that. Why is this a national park? Well, it's stunningly beautiful, but it's mostly because of the efforts of these two gentlemen. The guy on the left-hand side, that's Teddy Roosevelt there. He was president of the United States way back, right? And the guy to his right, his name is John Muir. And John Muir was a naturalist. And John Muir had plenty of faults, I'm sure, but one of them was not loving nature. One of his faults, actually, it wasn't a fault to love nature. He loved nature. Anyway, he's the one that promoted this idea, is like, this place needs to be preserved for all humanity and into the future for future generations as well. And so Muir is the guy who pitched the idea to Teddy Roosevelt. Teddy Roosevelt was all about preserving nature and making national parks early on in the start of putting national parks into the landscape for people to enjoy. Now, this is one of those places that everybody goes to Yosemite if they get a chance. It's best now I think you have to buy tickets to get there now. So it's a place that easy for people to love to death, okay? But anyway, this is Yosemite National Park, and that is El Capitan here. And what I want to do is, you can see in the distance behind Teddy Roosevelt there, that is one of the waterfalls here, and I think that one is Yosemite Falls. It's the highest waterfall, as I think it's the highest in the United States, and certainly it may be in North America. But that is Yosemite Falls there, El Capitan on the right-hand side. I'm going to show you a short video of Yosemite Falls, just because I can, because I was there about a year and a half ago here. So it was a really spectacular sort of day. That's my photograph actually on the right-hand side of El Capitan when we visited about a year and a half ago. That was around Christmas time, 1919, I think it was. Yeah, 20 kind of should be probably scratched off his calendar or something.
Some waters.
I want to show you another batholith next here. And so that batholith, in fact, is in South America here, and that's at Rio de Janeiro. And so that is in Brazil. And you can see here a granite stock that forms that Sugarloaf Mountain there. They call that Sugarloaf Mountain. There's another one here that has a statue of Jesus of Rio de Janeiro here, but that's Rio de Janeiro, and that's one of the trademark sort of things at Sugarloaf Mountain here. Spectacular place. When we look at smaller sorts of features, we can look at the Notch Peak stock, and that's made out of granite as well. And in this photo, you can't really see the stock so much, but you can see a sill that's associated with it. So that's the image on the right-hand side. That's a sill that shot off of that stock. It's a much smaller feature, and so in fact, Notch Peak, that feature that's in the back there, is not made out of igneous rock. That's actually made out of sedimentary rock that has been intruded around it. So the actual Notch Peak stock itself is off to the left-hand side here. It forms the mountain that's far in the distance there, but it's not the high mountain that you see on the right-hand side of that image. But that is where Notch Peak is, and so Notch Peak has got a couple of notches in it there, and so that's the south notch right there. It's a granite. Technically, it's a quartz monzonite, but you guys don't need to know about monzonites yet, but you're going to find out, if you're a geology major, you're going to find out later that monzonite is something that lacks a lot of quartz. And so in this case, it's loaded with potassium feldspar, but that is where that occurs. And because it's small, and it's roughly, it's smaller than 100 kilometers square for sure. It may be like 5 or 6 kilometers by 5 or 6 kilometers, and kind of roundish in shape if you look at it from above. And so that's the Notch Peak stock there. Next, you've already seen this kind of before, not this image especially, but there is Devil's Tower. It's a volcanic neck, as you well know. So that is a volcanic plug, is another term that some people call it. Now, neck meaning that it rises up and would have been at the head of that volcano, right? But a plug would have filled that volcanic opening essentially, and that's where it essentially cooled in place. And so volcanic neck and volcanic plug mean the same thing to us. And so that is Devil's Tower here. It's a national monument, an older photograph there. Got to visit here about 10 years ago, something like that, and maybe 8 years ago. This is Devil's Tower from up close here. There's a trail that runs all the way around it. Easy to walk around, not very big, in fact. And you can actually see where the columnar jointing is there. And so this is up close, and you can actually see what looks like where the bear claws were scratching at this thing, right? And the people were at the top of that. Well, in fact, climbers used to climb up all this all the time. And I think they've kind of restricted that nowadays because it's considered to be a sacred site for the Shoshone or for the Sioux nations. But anyway, down below here, that's going to be the stock. And so this is an unusual rock. This is not granite in this case. It's not a rock type that you have to know. Just like quartz monzonite is not a rock type you have to know. This is one called phonolite. And so phonolite is actually, it's funny how it got its name actually. when you take a chunk of this rock and you hit it with a hammer, it has a tonality to it. And so it's like, boom, it rings like a bell. And so that's what phonolite is. And so that's a phonolite right here in Devil's Tower. And so that's a volcanic plug, or you want to call it a volcanic neck, you can call it that as well. This is some of the signage there in the National Monument, and it shows you that the tower was composed, in fact, of that rock called a phonolite, but it in fact would have had the stock down below, and then it would have been covered by the volcano above. And so here you can see sort of an artist's illustration of what that would have looked like some 50 million years ago is what they estimated at here. And so that's the plumbing system. So it would have been the roots of that volcano at one point. So that's a volcanic plug or a volcanic neck. And so up close, you can see the columnar jointing here again. And again, it cools and it fractures essentially. And so those are all fractures. And those pieces wind up being piled up around the bottom because they'll break off every once in a while. People, when they climb this thing, they like to get in those cracks and climb up what they call chimneys and cracks and things like that. But, I don't know that they can do that anymore. But on the right-hand side, you can actually see the Google Earth image for this. And looking down, you can see the shadow that it casts across the landscape to the north there. So this would have been taken probably early in the afternoon. But you can see that it has some height to it. I think it's about 800 feet high, something like that. That's what I recall anyway. So it's not the only one of these features on Earth. In fact, there's another one close to Four Corners. And so Four Corners is where four states come together and form a intersection essentially right there. The boundaries all come together. And so you can stand on one spot and stand in four states simultaneously. And that is Arizona, New Mexico, Colorado, and Utah, where they all come together at that point. That's called Four Corners. If you drove to the south and east from Four Corners, you would see this feature. That's called Shiprock. That's obvious. It looks like a big ship in the distance, and it's huge. It's like 1,000 feet high. And so you can see not only Shiprock, but in fact, you can see some of the dikes that go into Shiprock as well. So on the right-hand side, I show you another Google Earth image that shows the dikes coming into that feature here. And you can see the volcanic neck is where the two, let me do it properly here. So where the two come together right there is that's where the volcanic neck is. And that's the volcanic plug, in other words. So the dikes come across there, and in fact, in the next image, you can actually see there's a road that cuts across that dike, and here's where that road cuts across. And so this is the street view image of that. You can see some mountains in the background there, but in fact, Shiprock itself is over on the right-hand side of that dike here. And so, kind of a neat place. This is Navajo lands here, and it's a beautiful sort of part of the world out here. So that is Shiprock. That takes us through a lot of the things that we were expecting to see so far, like batholiths. We've seen volcanic necks. We've seen a couple of stocks. We've seen what dikes look like now. Let me show you what a sill looks like. And so this is actually a historical image from a place called Taylor Valley. It's in Antarctica. I've had the opportunity to go to Antarctica a few times, but I've never been here. And I'd love to go here at some point, but that is a sandstone. The lighter beds on here are called the Beacon Sandstone, in fact. And the dark areas, in fact, are a rock called dolerite. And dolerite is an unusual rock. We call it actually diabase in North America, but diabase and dolerite mean the same thing. And essentially, it's a rock that has it's a mafic composition, obviously here, because it's black, right? And it is not volcanic in origin. It's actually an intrusive rock, so you can see where it's shoved these other rocks out of the way and intruded laterally, and so that's a sill right there. And so that is what they call it, the Ferrar dolerite, but it forms a sill in this area. And so you can see some feeder dikes and things over above the green tent here on the left-hand side. And on the right-hand side, you don't quite see the feeder dikes and things like that, but that sill cuts across another valley there. And so dolerite and diabase have a finer grain texture than what gabbro has, but it's not quite as fine as what basalt is. And already you know that basalt is an extrusive, right? And so basalt and gabbro go together like this. This also is that intermediate sort of rock. You can call it a microgabbro, but it is very small crystals that form a gabbro-like rock. It's essentially the same composition. So if it's an intrusive and it looks like basalt, we call it a diabase, or we call it a dolerite if you're in Britain. And so that is the Farrar dolerite in Antarctica. And so you can see one of the main glaciers cutting across behind it over there. But this is in Taylor Valley on the left-hand side here. One of the most famous of all sills, in fact, is in Edinburgh. And so I hadn't thought about this before, but, I was doing a little bit of investigating. It's like, oh, I've been there. I've seen, and I had pictures of it. I was like, well, let me show you those. So this is, in fact, a place called Salisbury Crags. And we're going to look at this again at some point here, but Salisbury Crags there, you can see has a path around it here. You can see it from the north side, actually the northwest side over here on the bottom image, but the top image, you're actually on the trail looking off towards the south a little bit there, maybe the south and west. But that trail follows along where that cliff is. And so that cliff actually is made out of the same rock that the Farrar dolerite is. So it's a dolerite, they call it here. It's a diabase in American terms, but dolerite and diabase, same thing. It has a mafic composition. And again, it's going to be an intrusive. So as an intrusive, it would have squeezed in between sedimentary rocks. And in fact, what it squeezed into was a sandstone. So there's a sandstone. I think it's called the Balcula sandstone. And it's, but this is at Edinburgh. So on the bottom photo down here, you can see what it looks like looking back at, Holyrood Park is that whole area that's, Arthur's Seat is the mountain in the background there, though it's shaped like a saddle. And then Salisbury Crags is that slab or that sill of diabase that's in the foreground there. And so that is Holyrood Park, and you can see Edinburgh down below here, looking across the city there. It's the capital of Scotland. Other places, other types of rocks. I told you about the Henry Mountains already, and so here's the Henry Mountains, and it's a laccolith, and you can kind of see in the diagram on the right-hand side what a laccolith looks like. The feeder dike goes into it, pooches up the rocks over the top there. When you look at it from space, it looks like that photo on the left-hand side here. So it's a laccolith that has been deeply eroded. And when it eroded, it comes all the way down into that laccolith when it begins to erode away the rocks. But there were sedimentary rocks over the top at one point. And here in this next image, you can actually see where the rocks kind of lap up onto the edges of that laccolith here. And so that is the Henry Mountains here in kind of southeastern Utah. Spectacular place. If you ever get a chance to go visit this, get a Jeep and go out and see the world, I guess is what I'd recommend. It's one of the best things we have on this planet is we get a chance to go see these incredible features. And there's a geologic story behind many of them. So we make these geologic features into national parks. The Henry Mountains aren't, but this area right here is, I think it's on the southern part of Canyonlands. So Canyonlands is another place that's a national park. Spectacular. Okay, that gives us a pretty good background on what Plutons are. Plutons they're defined by their shape. They're defined on whether they've been concordant or discordant. Dikes will cut the beds that they intrude into, and sills don't, laccoliths don't, lopoliths don't, but batholiths do, and stalks do, and volcanic necks do, of course, as well. So that's our whole list of different kinds of Plutons, and now you also know what concordant and discordant mean. Either it cuts the beds or it doesn't cut the beds. If it does cut the beds, it's called discordant, and concordant if it doesn't cut the beds. So I think that's enough for now. So we're going to go on from here and take a look at volcanoes. So volcanoes, probably one of the more interesting topics in all of geology. I'll talk to you soon.